what scientists do is something like that's on this chart. You're making observations, looking at the world, maybe trying to figure stuff out by coming up with a theory or something, then testing that theory, and the idea is that if the experiment disagrees with the theory, you have to go back and try to get another theory. So, and then you have to publish. So actually, this is some stuff that I did when I was an undergraduate here. I did graduate in '93, but as part of a course that I took, which was a supervised research course I took in third year, I was looking at radial velocities of stars, so looking at Doppler shift of light from nearby stars using a telescope at Richmond Hill. And I ended up doing that same project as a summer project that I got paid for, so I got some course credit. I also got some money over the summer between my third and fourth year. And it took me a while to finish up the project and to actually get it published, but one of the things that happened is that one of the stars was varying in radial velocity. So I kind of had a hypothesis, I guess, that all these stars were just orbiting the center of the galaxy with a period of 220 billion years or something, or 220 million years, but one was variable in its, so I knew that if it's changing, its velocity has acceleration, so there must be a force on it. So I postulated that there was probably a force from an unseen companion that was pulling it, and it was actually a binary system. So then I published a single author paper a little while later, analyzing it more. I actually discovered the spectrum of the second star. It was very faint, but you could sort of see it. And then somebody else published this thing. So somebody read my paper, went out and looked for eclipses, didn't find any, but that's sort of how the process works. You not only make hypotheses, check it, discover stuff, but you also have to publish, and then other people will read your papers and then build on this work, and that's sort of how science goes along. The textbook talks about models, theories, and laws. So the idea with a model, that's sort of how we start problems, is we try to simplify things and come up with maybe a diagram or a description which models a situation in a certain scenario. And sometimes that's what allows you to make a computer simulation, actually. A theory is a more sort of general, testable explanation for lots of patterns. And then a law is usually something like F equals ma, some sort of very short, concise pattern which describes a certain action. But all of these is just the theory and the math that we're using to try to describe our experiments. Somebody asked this cool question about, there's new theories. Some people could come up with a theory, maybe a big war between blue and pink elephants that caused the Big Bang, that could be neither proven nor disproven. How do we know what happened before the Big Bang? Could have been elephants. So what makes a theory actually valid if we cannot disprove it? Is it just that the math works out? Well, it's a great question. So I think that theories should be testable and kind of useful. It's good if your theory helps people somehow, or at least eventually helps people. And there's also this thing called Occam's razor, which is the idea that it's sort of a guideline that if there's either blue and pink elephants have a war or not that, you choose the not that, because it's an additional complication which doesn't really help you. So, and I think Einstein said that you should try to make things as simple as possible, but not simpler. Okay, so sometimes it is a little complicated just because that's what the data is really showing you, but you don't need to add extra complications to your theories. Is electricity a part of classical physics? That was a great question. The answer is yes. There's something called classical electrodynamics, which doesn't involve any of this relativity stuff. I don't know, there's the SI unit system. This is the idea that there are dimensions of length and time and mass, and when you make measurements, you need a unit. So there's lots of different units for length, and there's lots of different units for time, and different units for mass, but there's these standard units that we like to use and that are defined some way by scientists in agreement around the world. There's also these little prefixes, probably good to know. Tera means 10 to the power 12. Kila means 10 to the 3. Do SI units need to be converted to in any situation? Not always. I guess sometimes people use kilometers per hour or something, but it's sometimes a really good idea to convert to SI just in case you're using like G is 9.8 meters per second squared, or a Newton or a joule is a combination of SI units, so it can be handy. We cannot convert between different dimensions. Like, you can't convert from time to length. That's absolutely correct. And why is it kilograms and not grams? I don't know. I think it's because in Paris they had an actual standard kilogram, which was the definition for a long time. And it was this big block, and they said, that's a kilogram. And it's just a historical convention, and it's kind of unfortunate. What time is it? We're getting pretty close. We've got about 4 minutes. What I wanted to do is do this little calculation. So this is a unit conversion idea, but what I want to know is gas cheaper if I drive to Buffalo? So, and it's really complicated because there's the US dollar, there's the Canadian dollar, and there's liters, which we use in Canada, and gallons, which are used in the US. And there's all these different conversion factors. So what we can do, I want to say, let's convert the price of gas in Buffalo to Canadian dollars per liter. So what I would say is that the price, which you can write down, is the one. I went to Seneca One Stop in Buffalo, and it was 2.99. And the units are, I'm going to call it US dollars, divided by gallons. So what we need to do is multiply this by things that equal 1. Because every time you multiply something by 1, it stays the same. So what equals 1? Well, I need a conversion that cancels out gallons and gives you liters, so that I can, and what is it? 1 gallon equals 3.785 liters. And what that's going to do is gallons cancels gallons, and you have a liters on the bottom. The other thing that equals 1, I need to get rid of the US dollars, so I'll put them down here. And I'll put Canadian dollars up here. And what do I know? I went on to the exchange rate, and I found that 1 Canadian dollar is 0.74 US dollars. And what that will do, I've set this up so that the USDs cancels with USDs. So what I get is 2.99 on the top, divided by 3.785 times 0.74. And then the units, the only thing left is Canadian dollars per liter. And when I did that, I got 1.068. That's the price in Canadian dollars per liter. So you compare that to $1.49. Ooh. I'm trying to circle something here. It's way cheaper, so much cheaper. And then another question you might ask is it worth it? If you fill up your tank for 40 liters, 40 liters times 1.4939 minus 1.068, that's the difference in Canadian dollars per liter. So you'll get a savings of about $15 per tank if you do cross-border shopping. Yeah, density there being mass per volume. So the unit of density is kilogram per meter cubed or grams per centimeter cubed. So it is correct to say one, you just had the units wrong. So there was that survey this morning, and I asked you something about an estimate of how many cubic meters of air are in here. So I'm just going to do a really crude estimate. I don't know how tall the ceiling is, but maybe 20 meters. We were just wondering, hey, the light came on. Did you notice that, John? It's on now. You turned it on. Okay, it was a switch. We thought there was a light burnt out, and I was wondering how anyone was going to get there and unscrew the light bulb, because it's just so high up. And then maybe 30 meters, I don't know. I didn't measure it at all, I just guessed completely. And I also looked at Google Maps, and I saw there was a 20 meters, so I kind of looked, I don't know, from above. Anyway, volume of a cylinder is the height times the area of a circle, so I got 14,137. But since it's only a wild estimate, and my input numbers were very shaky, I kind of rounded it to be just 10,000, about 10 to the 4 meter cube. So some of the comments that came in, can you have accuracy without precision? This is something from the reading. What if I told you my height is somewhere between 5 and 7 feet? Well, that's accurate. But if it was on a dating app or something, someone said, okay, my height's between 5 and 7 feet, it's not very precise, and so it doesn't really tell you. What you need here is a little more precision, right, if you want to figure out if you want to date the person. Can you clarify which are placeholders? In the textbook, it said 1,300 could have 2, 3, or 4. So what I tend to ask myself is whether or not the person who wrote it down was forced to write those zeros. So if you just write 1, 3, that's not 1,300. It's not 1,300, it's 13. So you have to put the zeros there. So I would call those placeholders, and I would say they're probably not significant. So maybe somebody rounded from 1297 or something. They just rounded to 1,300. I don't know. But if they had written 13.00, there was nothing forcing them to write those last two zeros. They could have just written 13. So since they wrote them, by choice, I guess, that makes them significant. They probably measured it. I don't know. And then if you got a significant zero after a bunch of insignificant zeros, then it changes those to being significant. So 1,300.0 actually has 5 significant digits, if that makes any sense. I want to talk for the rest of this class about uncertainty analysis and repeated measurements and distributions. So the basic idea here is that when you measure something and then you turn around and you measure it again, you often don't get the same answer. Instead, what you get is a distribution, meaning like a histogram. And the distribution tells you something about the number you're seeking. But you can never really find the number that you're seeking. Except sometimes you can. I guess if there's a basket that contains 3 apples, and someone says, how many apples are there? And you say 3, well, there isn't an uncertainty on that, I guess. But you imagine if a truck contains about 4,000 apples or something, and someone asks you how many apples are in the truck, it's much more difficult to give an exact answer. You're almost certainly going to be giving a number which is like an estimate. It has a distribution. Okay. So the reason here is not human error, because any number you measure in science, besides that 3 apples thing, is going to have an uncertainty. The distributions is actually what you're going for. Describing distributions is the point of experimental science. And you might want to reduce your uncertainty. That's good experimental technique, but you can never get it down to 0. And so don't bother trying to do that. You need to describe it. Describe your distribution. So we'll do a little demonstration here. I have a pendulum, and I want to measure its period, for example. So the period being how much time it goes to swing from one end back to the beginning. And so I could try to time it, like that, 1.28 seconds, but I want to maybe reduce my uncertainty a bit by actually measuring 5 and then dividing by 5. So I'm going to try to measure 5 oscillations of this and divide by 5. So watch me very carefully. Let's get it swinging here. I'm going to start the stopwatch. 1, 2, 3, 4. Okay, 2 things went wrong there. Does anyone have any idea? Anybody see? Yes? Yeah, I guess that's true. There was probably some air resistance. That's not one of the. That's a third thing. Any other ones? Yep.
The trajectory kind of changed because
It hit the table. That's definitely one of them. I think that's a bad thing. Anything else?
That's a random error or environmental error?
Yeah, that's like a not random error. I guess it would slow it down. Yes.
The speed is not consistent.
Yeah, the speed slowed down a little bit, but there's a really big mistake. Started circular motion. I'm actually asking about my measuring technique. We can try to get rid of some of those, but let's start this again at 0. 1, 2, 3, 4, 5. 6.78. Yeah, yes, any thoughts? That's exactly what I was looking for. You shouldn't start at 1. I should have started at 0. I actually only measured 4 things. So that's a human error. That's like an actual mistake. which was a stupid thing for me to do, which I need to correct. And that would have really given like a not random error. Okay, so there's mistakes that you can make, errors, and then there's uncertainty which you can't get away from. Okay, so we're going to try to get rid of our mistakes. We're going to try to make it not hit the table. I'm going to start at 0, and then we're going to start recording things, and I'll put it on the screen up here. So, ready? So we've done some work to try to get our experiment to make some kind of sense. Let's actually now try it. Just do our best. So. Get it swinging. Try to get rid of the circular motion and all that, okay? 0. 1, 2, 3, 4, 5. Okay, good. So I got 7.53 seconds. Let's do it again. Just to be good experimentalists, let's do it a few times. 0. 1, 2, 3, 4, and 5. I got 7.38 seconds. Don't forget to put units. Oh, I hit the table. Maybe not so much amplitude this time. 0, 1, 2, 3, 4, 5. 7.47. And then just patiently, let's do it one last time. Oop, take it to 0. Stop you. 0. 0. 1, 2, 3, 4, and 5. 7.4. So I get different numbers every time I do this. And maybe it's because of the air resistance, maybe it's because of the little circular motion, maybe it's that amplitude. There could be a lot of little reasons. Maybe just my reaction time of pressing the button. I don't know. Basic idea here is I could have made a histogram of those 4 measurements. What a histogram is, it's a graph of, on the horizontal axis, you list the measurement that you're making, which is time in this case. So I put time there. And on the vertical axis, you put the number of times that you made that measurement. So it just turned out that I made a whole range here, and you have to bin the numbers, right? So one of those numbers is between 7.35 and 7.4. One of those numbers is between 7.4 and 7.45. So I got 111. That's my histogram. But if I had just kept on repeating that experiment, I'm not going to do it, but you can imagine me just doing it again and again and again. What if I did it 8 times? Well, the histogram would eventually look like this. If I did it 12 times, the histogram starts to look like this. So now I've got 5 measurements between 7.4 and 7.45. And I'm sort of getting a better idea of what probably this T5 number is. 16 measurements, okay, et cetera, et cetera, et cetera. So it turns out when you make lots of measurements and you're doing things carefully, you get a distribution which is called a Gaussian shape. It's sometimes called a bell curve, sometimes called a normal distribution. It's got a very specific mathematical shape. And you try to get that shape to fit through your histogram. It's a fit of a histogram. Okay? And it was invented by Gauss. It's actually a funny story. Gauss was this guy, 1777 to 1855. He did a lot of math, invented a whole lot of math, but he also was put in charge of things like the Göttingen Observatory. And apparently all the students and the people who worked at the observatory were terrified of this guy, because what would happen is they'd go up and they'd make measurements of some asteroid or something, and they'd get exactly what its azimuth and altitude was night to night. And when they would bring back the data, it didn't go in a little straight line. It was kind of jumping around. And he would yell at them and say, "You're not being careful enough. You're not being careful enough. You should be able to get this, right to the best precision." And so finally he finished admonishing them and said, "Get out, get out." He threw everyone out of the observatory, went up and did it himself. He spent the night taking measurements. And then he didn't look at anybody when he exited the observatory. He just went straight down to his office, closed the door, and about a week later, he published this whole thing about how you can never get rid of uncertainty altogether. You have to make a distribution, and it's called a Gaussian. And the students all kind of felt a little vindicated, I think, which is that you can't get away from this. This is distribution. There are other distributions, like there's a Poissonian distribution if you're measuring small things that can't go negative. There's a few other distributions that are really useful in science, but the one that comes up most often is the Gaussian. And here's actually two completely unrelated examples. Way back in 1886, someone went around and measured the heights of a bunch of people in London, made a histogram, and it's a Gaussian. Kind of weird. This is the distribution of U.S. stock returns between 1928 and 2018. And again, just on the, you can see when a stock is bought and stock is sold, how much did they make? You can plot it on a histogram and you get a Gaussian. Comes up all the time in science. So it's useful. And that's what I'm going to assume for all this uncertainty analysis, is that you've got normal statistics. So, oh, yeah, Parmita. So this is another one. There's something called a random walk. I have a student volunteer, Parmita, who is going to show you the plinko, as they say. So you pull this, and John just wanted me to tell you that the hole that drops these balls is over here. So you have to, I don't know, you have to get going. She's going to drop the balls, and they're going to do a random walk down. I guess you just pull the yellow thing on the side. Just pull that out. There you go. You can see what you're doing over here. Just keep going. Try to drop all the balls. Yeah. I think they're falling through here. Oh, there we go. Okay. How come they're not falling in the middle, John? Yeah. Okay. Thank you so much. Awesome. We could try it again, sure.
It'll take me just a minute.
The final distribution is described by a Gaussian, although that looks more like a Poissonian distribution, actually, because it hit the end. It turns out, plinko, that's another funny story, is that demonstrations, what is it? So in biology class, the demonstrations always smell bad. In chemistry class, the demonstrations always explode. And in physics class, the demonstrations never work. So, but it was a good job. So, okay. What I'm going to do is try to make a measurement here of what are these individual uncertainties, and I'm going to do it carefully. So the first thing you do is you estimate the mean. So this is called estimated mean. And it's very simple. It looks really complicated with all these sigmas and everything. You just add up these numbers and divide by the number of numbers. So n here equals 4. And so you say that x estimated mean is equal to 1 over 4, is the 1 over n, times the sum of all these numbers, 7.53 plus 7.38 plus 7.47 plus 7.43. And you get, it's equal to, I got 29.81 divided by 4, so I get 7.453 seconds. That's your first step. And now, this is going to be your uncertainty. So we're going to estimate the uncertainty as being what's called the standard deviation, which is the square root of 1 over n minus 1 times the sum of the squares of the differences between the numbers you got and the mean. So I'm going to take this number and plug it into this. So I have to go to the next page, unfortunately. So I've run out of room on my PowerPoint. It goes, again, it looks really nasty, but what you're going to do is sigma is equal to the square root of 1 over 4 minus 1, so it's going to be 1 over 3, times 7.53 minus, what the heck was the mean? 7.453. Oop. Sorry. There might be actually a button on your calculator which does this, but I'm just going to do it the old-fashioned. And then I'm going to add it, because this is the sum, to 7.38 minus 7.453 all squared plus 7.47 minus 7.453 all squared plus 7.43 minus 7.453 squared. And then don't forget to take the square root of that whole thing. So it takes a little bit of math. I got 1 over 3 times, I got 5 point, these are, when you square these numbers, they get even smaller, times 10 to the minus 3, plus 5.33 times 10 to the minus 3, plus 2.89 times 10 to the minus 4, plus 5.3 times 10 to the minus 4. And then I'm going to add those all up, take the square root. I get sigma equals the square root of 0.012 divided by 3, and I got 0.0635, and it's in seconds. So, and I can round that off, sigma equals 0.06 seconds. So remember I asked you to estimate what the uncertainty is, and you got 0.05, a lot of you did. So this is the real answer. So what I would do is back here I would say plus or minus 0.06 seconds, plus or minus 0.06 seconds. So each individual measurement, now that we have all this, so is actually, so this is uncertainty in each measurement. Okay. So then there's these error propagation, the uncertainty propagation rules, which are in your reading. But basically, if you have an uncertainty in x and you have an uncertainty in y, and you're trying to add those two numbers together, then there'll be an uncertainty in the result. And so there's a rule which says you add the squares of the uncertainties and take the square root. It's called adding in quadrature. So we would say, and it also works for subtracting two numbers. If you're multiplying or dividing numbers, then it's the same rule, or looks the same, but instead of adding the squares of the uncertainties, you add the ratios, the squares of the ratios of the uncertainty to the number itself. And that gives you the ratio of the uncertainty in your final answer to that answer. And so I've given you an assignment where you can kind of practice some of these things. You can really only figure it out through practice. There's multiply by the exact constant rule. So if x is an exact number, then you just take the absolute value of that exact number and multiply it times your uncertainty in y in this case, and you get the uncertainty in z. This works really well for like unit conversions or something. If you're converting from meters to kilometers, you just divide your uncertainty by 1,000 as well. And then there's an exponent rule. If you're raising something x to the power of n, and you have an uncertainty in x, then this is the uncertainty in that x to the n. It's n times the fractional uncertainty. Okay, and I have an example where I'm going actually, where did my pen go? Oh, here it is. This thing always rolls on me. What I wanted to ask you is, what's the uncertainty of the mean? And you can figure this out. We'll use the equation for mean. Mean is the same thing as average. You put a little bar on it. You get x1 plus x2 plus a whole bunch of things plus x sub n divided by n, right? So this is x, we'll call this x sum divided by n. So this is an exact number, 1 over n, times x sum. This is an exact constant. Because hopefully we know how many times we measured it. So the uncertainty in x mean is equal to 1 over n times the uncertainty in ux sum. And the uncertainty in ux sum, we can use the sum rule, is just going to be the uncertainty in x1 squared plus the uncertainty in x2 squared plus plus the uncertainty in xn squared. Take the square root. So I used a rule there, and I used another rule here. This one was, I think, rule number, I called it number 2.1 or something like that. And this is rule number 1. Anyway, but if it's always the same, they all have the same uncertainty, u sub x, and this is just equals to the same thing, ux squared plus ux squared plus plus ux squared. And how many of these are there? There's n. Right? So this just equals the square root of n times, ux squared. So, and then you can distribute through, you get square root of n times u sub x, this is positive. So the uncertainty in ux bar is equal to ux sum divided by n. It's the square root of n divided by n times ux, which I think turns out to be ux divided by the square root of n. So that's your main equation there. The uncertainty in the mean is the uncertainty in the individual measurements divided by the square root of n. And that's a useful thing. If you make many independent measurements and you average them all, the uncertainty in that average you take is a factor of the square root of n less than the uncertainty of your individual measurements. And that's why we take lots of measurements and average them. It's because we want to reduce the uncertainty. So, and then these are the real rules which I actually do care about for significant figures. That is what people use in science, is that uncertainties should be specified to either 1 or 2 significant figures. And when you look at journal articles, people tend to do 2, just to be on the safe side. And then the second rule is once you know your uncertainty and you specify it to 2 or 1 significant figure, the most precise, like tens column of your uncertainty, that's what you should round your number to, your value to. Make sense?